Okay, well, this is chapter 3, section 7, optimization problems. These are story problems where we're trying to find maximums and minimums. Um, as I mentioned in a previous section, it's a key idea to the way we do business, the way that we discover things, scientific approaches, is to maximize and to minimize whatever it is that we're investigating. So we're going to practice doing that, and of course that's going to involve the derivative and either the first or the second derivative test to show if we have a relative max or relative min. While we are working these problems, we want to make sure that we are coming up with a max or a min, not just that it seems that way, but that we prove that by either using the first or the second derivative test. Now, because these are story problems, the trick, as you guys have always encountered with story problems in your algebra days and pre-calculus days, would be to come up and interpret the problem and model an equation or a function after it. That's the same here. We want to be able to come up with the problem with the function that works for what the problem is talking about. So we'll start with a couple simple examples, and then we'll work our way to ones that may be a little bit more involved, and along the way we'll come up with a nice strategy to do this. So first things first. All right. Example A. It says solve here. Find the dimensions of a rectangle with perimeter 100 feet whose area is as large as possible. Now, as I would always suggest with anything that involves some kind of a geometric idea, is to draw a diagram, label, and then determine what you want to use for your variable and set up your function based on the information in your diagram. So since it's a rectangle, draw this out this way. We know opposite sides are congruent. It says that the rectangle has a perimeter of 100 feet. That means all the way around is 100 feet, which means halfway around is half of 100 feet, or 50. So if I let x, let's say it's the width, then 50 minus x would be the length. So I like the label stuff, and that's the way I've got this set up. Now we are trying to maximize the area. Well, area of a rectangle is easy, and that's the function that we're going to use here because we're trying to maximize the area. So the area is length times width, or in this case, since my variable is x, I'm going to write a of x is equal to length times width, x times 50 minus x, or 50x minus x squared. Now, before I get too crazy here, I want to make sure I don't have any restrictions here on what x can be, and I definitely know that x has to be greater than 0. I mean, I can write greater than or equal to 0, but if it's equal to 0, we don't have a rectangle. We have a line segment. We have a trivial rectangle. So in this case, I'm going to let x be greater than or equal to 0. Now, are there any restrictions? Well, halfway around is 50, so I would think that x would have to be between 0 and 50. And again, I put the endpoints on, but at the endpoints, you're really not going to get anything that works because we're trying to maximize our area. So you could just as easily, it said 0 is less than x is less than 50. So let's take a derivative, because that's how we define our max and mins. So the derivative of 50x minus x squared is 50 minus 2x. I'm going to set 50 minus 2x equal to 0. I get x is 25. So here is where I use the first derivative test for a prime here. Here's 0, here's 50, that's my domain. And 25 would be dead red right in the middle there, so that's 25. So I'll test this. I'll take a number from here, like, let's say 1. Plug 1 in here, I get a positive. Take a number over here, let's say, I don't know, 40. 50 minus 2 times 40, that's negative. Increasing, then decreasing, I have a relative max, which is good because a max would give me as large as possible. So now, I'm sure it's a maximum. I know that x is 50, and of course if x is 50, x is 25. So since I know x is 25, I know that 50 minus 25 is going to give me 25. This rectangle is actually a square. Just not cool, baby. And so that gives me that the dimensions are 25 by 25, and this is in feet. So to maximize the area of the rectangle, the dimensions should be 25 feet by 25 feet. Oops, 25 if I can write it. And there is my answer. Now again, I try to stress this back as algebra, that when you do a story problem, your answer it shouldn't just be circling a number or putting the unit down and circling it, but you should answer it in a short sentence. It doesn't have to be real long, a lot of writing and such, just a short sentence, and make sure, of course, of your units. Make sure that the answer kind of makes sense. This is a pretty straightforward one, but as it turns out, for a perimeter, if you were, let's say you were going to put up a garden and you were going to put some fence around it and you wanted to maximize your garden, and you had 100 feet of fencing, this would tell you to maximize the area of the garden, you should make the garden 25 feet by 25 feet. I mean, you could make it, 5 feet by 45 feet and have a long skinny garden, but it wouldn't have as much area in there. So anyway, here we go. That's the first example. Here's another example, also with a rectangle. As I mentioned, these first couple are a little bit easier than the others. It says a rectangle has its base on the x-axis and its upper two vertices on the parabola y equals 12 minus x squared. What is the largest area of the rectangle can have, and what are the dimensions? All right, so again, it really would help if you have a diagram of what's going on here, especially since they give you a parabola. So I'll do my best to come up with something halfway decent here. Okay, so let's see. My vertex would be at 0, 12. 1, 2, 3, 4, 5, 6. Well, I'm going to have to go by twos here. And let's see. Let's just make these ones. 2, 3, 4. 1, 2, 3, 4. I've got symmetry with this graph because the axis of symmetry is the y-axis. Let's see. If I set this equal to 0, my x-intercepts would be plus or minus the square root of 12, plus or minus 2 squared root of 3, about 3.4. So about here, and negative 3.4 about here. So my graph is going to do something like this. That's the parabola. Not very good. Hopefully you can follow this. And how's my rectangle sitting? Well, my rectangle is sitting like this. Two of the vertices are on the parabola, and the other opposite side there is on the x-axis. It says its base is on the x-axis, and its upper two vertices are on the parabola. Now, I don't know what the x is, or what the x's are, or the y values are going to be, but I do know that it should fit something like this. Now, this x value I don't know. I'll call this x, so this point here would be x, and then it would be the y value. But what is the y value on this curve? Well, the y value on this curve is 12 minus x squared. So if I plug x into there, I get 12 minus x squared. So this is x. This distance here is 12 minus x squared. So that means my base is twice x, it's 2x, and my height is 12 minus x squared, because it says what's the largest area again, so I got to use the area formula. So a of x is equal to 2x times 12 minus x squared. Now, do we have any restrictions on x? Well, absolutely. X is not going to be negative, and it can't go past the square root, 2 square roots of 3. So my x value here is between 0 and this this guy right here, this x-intercept, which I think was 2 square roots of 3, or about 3.4. So we have that restriction there. I'm going to go ahead and multiply this out. This would be 24x minus 2x to the third. So I'm going to take the derivative. That would be 24 minus 6x squared. I'm going to set 24 minus 6x squared equal to 0. I'm going to get 6x squared is equal to 24x squared is equal to 4x equals plus or minus 2. Well, x can't be negative 2, so my only critical number here is x equals 2. So I'll draw out my number line and use the first derivative test to see if it's indeed going to give me a max or a min. Here's 0. Here's 2 square roots of 3. 2 would be about, I don't know, maybe about here, approximately. Take a number from here like 1, plug 1 in, it's positive. Take a number from here like 3, plug 3 in, it's negative. So it's increasing, then it's decreasing. Yep, that's going to give me a max. My max is when x is equal to 2. So if x is equal to 2, that means my height is going to be 12 minus 2 squared, which is going to be 8. So what's going to actually look like, here's 2, it's going to actually kind of look more like this for a rectangle there. So this is going to be 2 here, so that means the base is going to be 4. So all of this is 4, and then this was 8. So it's not a square this time, it's a rectangle with comparing the length and the width, or the base and the height, kind of a 2-to-1 ratio, 8 and 4. So it says, what is the largest area that the rectangle can have, and what are its dimensions? All right, the largest area of the rectangle, hopefully you can see that okay, of the rectangle is, let's see, this is 4 and this is 8, so it's 32 square units. The dimensions should be 4 units by 8 units. I'm not going to write the U down, just 4 by 8 like that. And there's my answer. All right, hopefully you're starting to catch on to this. Now I do have a strategy here that I'm sure you can find in just about every textbook. And there it is. Identify all quantities and quantities to be determined. And it says, when feasible, make a sketch. Well, as soon as you see the words when feasible, you know I probably copied this down off of something, because that's not how I typically talk. Make a sketch. I always think a sketch is going to be useful whenever possible, and in a lot of these problems it will be possible. Then write a primary equation for the quantity that's to be maximized or to be minimized. Some geometry formulas are used, and of course those are in the book or in the inside covers of the textbook, or you can just Google that if you need to. Reduce the primary equation to having one with a single independent variable. Now, in my first 2 examples, it was pretty simple. I had 2 variables, I had x and y, but as it turned out, I was able to easily write one of the values, in this case with the perimeter, so that everything was in terms of x, both unknowns, and the same thing here with this equation. It allowed me to figure out what the y was in terms of x. But sometimes you may have to come up with a secondary equation so that you can make a substitution into that. And that's what step 3 is talking about here. We'll probably come across one of those here in just a bit. Then, make sure of your domain. I did that in both of the first 2 examples, so that you're not using values that don't make sense. And then, of course, find the max and the min, using what we've learned in the first half of chapter 3. Again, definitely show either the first or the second derivative test so that you are backing up that it's maximum or that it's minimum. Okay? Now, here's another example. Okay, let's see if I can get that. There we go. Now it says, an open top box is to be made by cutting congruent squares of side length x from the corners of a 20-inch by 25-inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? Okay, see if I can kind of show you what I'm talking about here. Let's say that this piece of paper here is my, 20-inch by 25-inch sheet of tin. Well, I'm going to get messed up on that one for sure. And what they want me to do is cut out squares from each of the corners, congruent squares, so that this square will be the same size as this square when I cut it out. And I do that for all 4 corners. So we're going to grab some scissors, and I'll see if I can show you that with a demonstration of my paper cutting prowess. Let's see. Oh, already tore it, so much for that. So much for my keen paper cutting skills. I think my grandkids probably can use a pair of scissors more correctly than I can. Okay, this is pathetic. All right, so now I cut out my 4 squares from the corners. All right, so let me get rid of those, and then I have this. Well, let's see if I can tune this up just a little bit. That looks so bad. So now I have this. You see how the corners are cut out? And now I'm going to bend up these corners, or these sides here, and I'm going to form a little open top box here. Used to do this in grade school. And look at this thing here. Does that look professional or what? Do you see how I have the open top box? Now I cut out corners that were this size. If I cut out bigger squares, my base would be smaller, but it'd be taller. So I want to get that perfect happy medium where I have the right size base and the right size sides here, so that I get a maximum volume box here. The best thing about this is now I can put my corners in there and I can just scoot her to the side. So that's what I'm trying to do. Nothing like visual aids here. So now I'm going to kind of draw it out over here. Here's my, let's see if I can, this is supposed to be 25 inches and this is 20 inches. And I'm cutting out a corner here. Let me use a colored pencil here to kind of show that. There's a corner, there's a corner, there's a corner, there's a corner. And then I'm going to fold it along these dotted lines here, because what's happened now is that if these corners are cut off, disappears mostly. There we go. And I have this. I bend up those sides. Now remember, we don't know how big these corners are, so I'm going to call this X and this X. So this would be X and this would be X all the way around, because they're supposed to be congruent squares. And do we have any restrictions on X? Well, X has to be positive, and it can't be more than halfway across the shorter side, so it would have to be between 0 and 10. Because if I cut out something like, let's say 9.99, it would almost go all the way. There'd be just a little skinny side to bend up here. So in this case, it's going to be between 0 and 10. That's my restriction here, my feasible domain here for my variable. Now, what do we have for sides? Well, the height is X, because that's going to be bent up. But how long is this part right here? All of this was 25 all the way across. And I cut off X and I cut off X. So this should be 25 minus 2X. And similarly, all of this was 20. So if I cut off X and I cut off X, this should be 20 minus 2X. So I'm thinking I can get my volume. Now, a volume of a prism like this is going to be length times width times height. So I'm going to say V of X is equal to X times 20 minus 2X times 25 minus 2X. And those would be my length, width, and height, not necessarily in that order. All right, so now that's the guy I'm going to try to maximize. That's my primary equation, and it has a single independent variable, X, so I don't need a secondary equation. I can go right after this, and I am not going to use some kind of weird product rule. I'm going to multiply all this out, and then just take the derivative of the polynomial. I think it'll be easier that way. So if I multiply and I do FOIL here, that's going to give me 4x squared times x is 4x to the third. That's going to give me minus 40. Minus 50 is minus 90x. So that'd be minus 90x squared when I multiply by the x. And then 20 times 25, that's, what is it, 500? So that's going to be plus 500x. Yikes. So I'm going to maximize this guy. I hope I have written this down right. All of a sudden I got this really bad feeling. Minus 40. No, that looks right. So that's going to be v prime of x is going to give me 12x squared minus 180x plus 500. Alright, I'm going to set this equal to 0 and find my critical numbers. We're having some fun now. Let's see, can we get through? We can divide through by 4. 3 doesn't go into 500, so let's go divide through by 4. And that would be 3x squared minus 45x plus 125 equals 0. Oh, I hope this factors. I'm going to be mad if it doesn't. 25 and 5 maybe? Ooh. God, no, I don't think that's going to work. 25 and 5 does not look like it's going to work here. I'm thinking I messed up because I thought I had one that factored. 25 and 5. Oh, I should definitely have done this prior to working it out now. Let me make sure of all my calculations here before I have to redo this problem all over again here. That would stink mightily. 20 by 25 sheet of 10. So that's 20 minus 2x, 25 minus 2x. So that would be 4x squared, 4x cubed. That'd be minus 40 minus 50 is minus 90x squared. And then I have 2 times 25 is 50, 500x. So if I take the derivative, please let me find a silly mistake here. I'm not set it equal to 0. I divide it through by 4. Definitely 45. Definitely 125. This is not going to factor. I thought for sure it was going to be 25 and 5 because 125 just has 3 factors of 5. 25 here. 5 here is only going to give me 40 in the middle. This has got to be a 160. What am I messing up? So that's minus 40x minus 50x is minus 90x. Should have done this ahead. So I have to use the quadratic formula. X equal to the opposite of b, which would be 45 minus the square root, plus or minus the square root of 45 squared, which is 2025. I'll double check that. Minus 4 times 3 times 125 all over 2 times a, that'd be 6. Let me grab Mr. Calculator wherever I've done with him. Doggone me for being ill prepared here and having one that I thought was going to work out just fine. Let's see, 45 squared first. Let's make sure of that. 2025 minus, let's see, 4 times 125 is 500 times 3 is 1500. That's 1500 is 525. Doggone me. I thought for sure I had gotten this to work out. 45 plus or minus the square root of 525, and that's all over 6. Now the square root of 525 is, let's see, 25 goes into that. Let's see, that would go in, well, let's see, 21 times, yeah. So this is 45 plus or minus 5 square roots of 21 all over 6. Let's see. Now, this number, the square root of 120 or 525. Let's see here. Is like 20. This number here is like 20. Almost 23. 23, and if I was plus, and 45 would be 68 divided by 6 is more than 10. So my only value here that's going to work, my only critical number here that's going to work is x equals 45 minus 5 square roots of 21 all over 6. Well, it's time to approximate this. So 45 minus 5 times the square root of 21 divided by 6. I'm getting 3.681. Draw my number line out. What a mess I've made of this. So here's 0, here's 10. This is for V prime. And about here it'd be 3.681. I take a number from here like 1. I go back to my derivative. That would be 12 minus 180 plus 500. That's definitely positive. To take a number over here like, let's say, 9. So that's going to be 12 times 81 minus 180 times 9 plus 500. I get negative 148, so this is negative. So it does maximize. That's increasing, that's decreasing. So it says, how large should the squares be to make up a box that holds as much as possible? Well, fortunately, that's this value. And this is in inches, right? So to maximize the volume of the box, the side length of the squares should be 3.681 inches. And there's my answer. Now, you guys check my work, because I'm not redoing this video. This is long enough as it is, and I haven't even gotten to a couple more of the examples. You guys check my work on this, and if I've messed up, you bring it to my attention, and then I'll go ahead and make a correction, and I'll give you credit for the correction there in the video. All right. I think that's good. I've looked at it 3 times. I think that's good. So I'm going to go on to another example and hopefully do a little bit better. Here we go. It says a rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single strand electric fence. With 800 meters of fence at your disposal, what is the largest area you can enclose and what are the dimensions? So in this case, we've got a river here. I don't have a blue colored pencil here, so I'm just going to put the side. This is the river. And we are going to put some fencing and make a rectangular a plot of farmland. So let's go out like this, over to here, over to here. And I have a rectangular piece. Now I don't have to put fence here because of the river here serving as my boundary. Now I have 800 meters of fencing, so if I use X meters here, I'll use X meters here, which means that this would be 800 minus the 2X meters that I used for the other 2 sides. And this is a little bit simpler than the last one. I'm certainly going to have a simpler equation. It's going to be quadratic. Now, do we have any restrictions on what X can be? Well, these 2 sides here, it can't be more than 400 or equal to 400, because then you wouldn't have a side here on this side. So I'm saying that X has got to be positive, but at the same time it has to be less than 400. All right, so now what I'm going to do here is I'm going to find the area as X times 800 minus 2X being my function. That's my primary function. So this is going to be 800X minus 2X to the second, and a prime of X is going to be 800 minus 4X. Now I'm going to set 800 minus 4X, much simpler problem than the last one, because I can see this is going to solve nicely. And I'm going to get 4X equals 800. I'm going to get X equals 200. So I'm going to draw out my number line here. I'm not going to jump right away to the conclusion that 200 has to be my answer. I'm going to double check here. This is 0. This is 400. This is A prime. 200 be right in the middle. And what do we have here? Well, if I take a number from here like 1 and plug 1 in, I get 800 minus 2, plug 1 in here, into the derivative, I get 800 minus 4 is positive. If I take a number here like 300, I get 800 minus 4 times 300 would be 800 minus 1200, that would be negative. So it's decreasing, so yes, I do have a max here. It seems like all the examples so far have been maximums, but we'll see what we can do here in just a second. And let's see now, that would mean that this would be 200. This would be 800 minus 2 times 200. This would be 400. So another 2 to 1 ratio on the sides here. So What is the largest area you can enclose? What are the dimensions? The maximum area that can be enclosed is, well, let's see, if this is 200 and this is 400, this would be an 8 with 4 zeros, would be 80,000 square meters, and the dimensions of the plot are 200 meters by 400 meters. And there's my answer. Definitely a little bit simpler problem than the last one. Now this final example that I have is a little different. First off, it's a minimum because we're going to try to minimize cost. It's really the only one that involves money that I have here for you, so we'll give this one a try. I think I'm going to probably need more paper than I've allowed myself to use here, but we'll see what happens. All right, here we go. An offshore oil well is located in the ocean, hopefully it's in the ocean, at a point W, which is 5 miles from the closest shore point, which is point A, on a straight shoreline. The oil is to be piped to a shore point B, which is 8 miles from A, by piping it on a straight line underwater from W to some shore point P. I'm definitely going to need a diagram, between A and B, and then on to B via a pipe along the shoreline. If the cost of installing pipe is $100,000 a mile underwater and $75,000 a mile over land, where should the point P be located to minimize the cost? Yeah, I'm going to need more paper here, I think. Here's my straight shore. Let's see. Let's do this. Here's my straight shoreline. And here's my oil well. And this is, what do we have here? Located at point W, which is 5 miles to the closest shore point, so that'd be perpendicular like this, which is point A, and this is 5 miles. Okay. Now, it's to be piped to shore point B, which is 8 miles from A. So we'll put B over here. This is not really drawn to scale. Well, we'll move it a little closer here so it looks like it's more drawn to scale. And this distance here is 8 miles. And it says here, 8 miles from A, by piping it on a straight line underwater from point W to some shore point between A and B. They call it point P here. So maybe it goes to here, point P. So they're going to bring it this way here. Let me go underwater in green. So they're going to pipe it to there, and then once it gets to the land here, then they're going to pipe it here to B, above ground, so it's going to be a little cheaper. Now, the key is the shortest distance from W to B would be this line, but that would be all underwater, and it's $100,000 a mile underwater. And, you know, do we bring it straight to point A and then bring it across? It says that there's going to be some point P that's going to minimize my cost. Now, I don't know the distance from A to P or from P to B. I do know that the distance from A to B is 8. If I call this distance here x from A to B, then this would be 8 minus x from P to B. And this distance here in green, I'm going to have to use the Pythagorean theorem. This would be the square root of x squared plus 25. Well, I'm able to keep it to one variable at least. It looks like I have one independent variable, so the green is underwater, and that's the distance in miles. The red is above water, and that's in red here. That's 8 minus x. That's the distance there in miles. And we have to minimize the cost. Now the cost is c. Now what do we have restrictions on x? Well, x, I'm going to guess here then, would be between 0 and 8. Now I guess it could equal point A if it came straight across. I'll put the equal to it. It could be equal to point B if they go straight underwater. So we'll make that as my domain here between 0 and 8 inclusive. And my cost would be in green here, it's that distance at $100,000 for each one of those miles. That's 100,000 times the square root of x squared plus 25, and then $75,000 at 8 minus x, so plus $75,000 at 8 minus x. Let's see, I have to distribute over here. I could do that, so I have, before I take the derivative, 100,000 times, I'll write this as x squared plus 25 to the 1/2, plus, now let's see, 75,000 times, what is that, 8? Should be able to do that in my head. I am so lazy. I get 600,000 minus 75,000x. Nice. All right, let's find my derivative. Time to go to a second pencil here. This one's starting to get dull on me. What do I do with my other pencil? Well, I guess it's this guy for the duration. I can't find my other pencil. And this is going to be equal to, let's see, I bring the 1/2 out in front, so that's 50,000 times x squared plus 25 to the negative 1/2 times 2x. Using the chain rule there, the generalized power rule. The derivative of 600,000 is 0, and the derivative of 75,000x would be 75,000, so minus 75,000. I need critical numbers, so I have 50,000 times 2x, that's 100,000x, all over the square root of x squared plus 25 minus 75,000, and that's going to equal 0. So I am going to add, well, actually I'm going to divide through by 25,000. So I have 4x all over the square root of x squared plus 25, and I'm going to throw it on the other side, so that will equal 3. So let's see, I'm going to have 4x is equal to 3 times the square root of x squared plus 25. I'm going to have to square both sides to get rid of the radical, so I'll come up to here. That's going to be 16x squared is equal to 9 times x squared plus 25. Distribute, I get 16x squared equals 9x squared plus 225. I get 7x squared is equal to 225. Divide by 7, I get x squared equals 225 divided by 7, or x is equal to plus or minus. It's not going to be negative. I get the square root of 225 over 7, which would be 15 over the square root of 7, which is 15 square roots of 7 over 7. So let's figure that out on Mr. Calculator here. So I have 15 divided by 7 to the 0.5 power. I get approximately 5.669. Now that's in between 0 and 8, so that seems like a good value here. I'm going to draw out my number line here. I'm not going to have space for my answer, but I'm going to have space for all my work here. Here's 0, here's 8. This is C prime for the cost. And about here, let's say that this is 5.669. And I take a number from here like 1, and I plug 1 into my derivative. Now it's way back over here. Way back to here. So that's 100,000 over about a little bit more than 5. 100,000 divided by 5 would be about 20,000 minus 75. That's negative. That's decreasing. Take a number over here. Let's say 7. Ooh, let's see. That's I'm going to have to grab the calculator again here. That's 700,000 divided by, and if I put a 7 in there, I get 49. I get 74. I get the square root of 74. Oops, let me clear out my window here. So what did I have? I had 70, let's see, what did I plug in? 7? So I had 700,000 divided by the square root of, what did I say it was, 74? And then I'm going to subtract 75,000 from that. Oh, let's see here. It's positive. So it's going to give me a minimum. So this value here, x, that's the distance from point A to point P in the direction of point B that I have to minimize the cost of this pipeline. So now all I have to do is answer it. It's just that I didn't give myself any space here to answer it. Let's see if I have a piece of scratch paper left. I do. So now, to answer it, it says where should point P be located to minimize the cost? To minimize the cost, of installing the pipeline, point B should be 5.669 miles from point A toward point, oh, this is point P. Yikes, point P. Towards point B. Messed that up. This is point P right here. All right. And that would be my answer. And that's a good example as well of the different kinds of problems where you're either trying to maximize or minimize. So I want you guys to give these problems a good try. And as always, practice, practice, practice.